the penultimate talk of the workshop. We have James Lee, who will speak about unimodular chain dominant.
Yeah, thanks for the invitation. Yeah, no problem. Welcome. Okay, so I'm going to talk about mostly low-dimensional things. In fact, mostly two-dimensional things, which, depending on the last time I was here for a high-dimensional combinatorics workshop. So I always feel like no matter what choice of dimension one makes, it's always disappointing to someone. So, yeah. Okay. So what's the? I guess to motivate the idea, let me try to connect two developments. One of Hersch in 1970, and then I will not write out Benjamini and Schramm because that's what BS means in this context. And a result of Benjamini and Schramm from 2001. So okay, what did Hersch show? If you take a take a Riemannian metric on the. I won't be talking about Riemannian geometry very long. So even if you, everything will be intuitive. So don't worry about this. Take some Riemannian metric on a two-sphere. Then here is a theorem. If one looks at the first non-trivial eigenvalue, which I will call lambda 2, even though they would call it lambda 1, of the Laplacian, then okay, it's at most 4 pi divided by the volume, or the Riemannian volume of the two-sphere with this metric. So this is the theorem. Is it clear? So how does one prove this? Okay, well, let's just write down the variational characterization. Okay, so I guess here, let's also do this and also this. Well, that's too much. Just mention that, I mean, every Riemannian metric on the two-sphere is conformal in the sense that we can write this metric as h. We can write h as phi times dx, where this is the volume element on the two-sphere with constant curvature, and phi is some say smooth density, so something non-negative. Okay, so it's just a rescaling uniformly of the underlying metric, and then you can write this just the variational characterization, minimize over functions to the real line of I'm going to go fast here. So first of all, I'm writing this as the for the energy of the function f. You'll notice it doesn't involve the metric h. That's because the Laplacian in 2 dimensions is conformally invariant. So there's a square and there's 2 dimensions, and so it doesn't matter. One gets the same notion of energy, but then the notion of the 2 norm will be different. It will be, it will have this phi in there. Okay, so we want to minimize that, and we want to do it over functions that are orthogonal to the all ones function. I'm sorry, to the all ones. I mean the graph setting already to the constant function, which just means that we want this to be equal to 0. So this is just the variational characterization of eigenvalues. Everyone is happy? Okay. So how can you prove a bound on this? Well, just take the standard mapping of the the standard embedding of the two-sphere into R3, and then what do you have? This is going to be basically the surface area. By the way, there may or may not be a constant. Depending on how you define your Laplacian, it might have a half in it or not. So there might be a factor 2 missing here, like depending on if you want the heat equation to have a half in it or not. But But if we just, so here now this is a map taking values in R3. So if I can just sort of evaluate the energy of this map, it will be, this thing is constant, it will be the proportional to the volume of the, this integral is over S2, volume of the 2 sphere. And you can also see that what we'll have here is that this is just, so of course the norm of f is 1. It's the standard embedding that maps the unit sphere to the unit sphere. So this is just integral phi squared, which is precisely the volume of this manifold, just the area. Okay, does this, it doesn't really have to, I mean, yeah, please ask if something doesn't make sense. I'll get to the punchline now, which is just that, so okay, we would have proved this, we want to prove this. So this is a 3-dimensional map, not a 1-dimensional map, but that's okay. If we could prove it for that map, just select one of the coordinates, they will give a bound like this. The numerator is 4 pi, the denominator is the volume. Everything is, does anybody see the one thing which is not great? Like, why doesn't this f prove the bound we want? This capital F? Yeah, I mean, it's because the, I mean, the function needs to be orthogonal to constant functions, and this f is, so I mean, if you look at what, right, this f is just the identity map. So this is just, right, I mean, this is just the center of mass of if you think about this phi as a density. So the point is, this is not 0. The center of mass is not necessarily at the origin. Okay, so now the clever idea is that this embedding is not really canonical. If you think about conformal maps, you could take any Möbius transformation, sort of pre-compose with a Möbius transformation, and it would be the same thing. So now what Hersh showed, which is not, it's a topological argument, is just that the family of Möbius transformation is rich enough to find one that moves the center of mass to the origin. Right? So it's you can basically choose some point on the sphere and do some inversion such that if you have to compose two things together, but then you can pull the center of mass towards it. So then some Brouwer fixed point argument says that you can choose an f for which is equal to 0. And all I want to do is say that you could think about this in a different way. Instead of trying to satisfy this, you could just, of course, you can also write lambda 2 as the minimum over f, and then here just project onto the orthogonal complement of the constant functions. Right? Like I could rewrite this characterization eliminating this condition, and then here just projecting onto the orthogonal complement. In other words, just subtracting off the expectation, just subtracting off integral f phi from this function. And then what you could do is you instead think about this as basically you're choosing, instead of thinking about choosing a Möbius transformation, you're choosing some other conformal metric on the 2 sphere. Every one of them gives you a bound on this quotient. The best one will be the one that doesn't waste any of the L2 norm, and so it will be this one that's sort of like this. Okay, so the whole point here is just that changing the metric gives you some information about the Laplacian. Okay, so that's some general. I mean, I think this is probably one of the simplest settings where something non-trivial happens. It's a cute argument. So now you can take this pretty far. So let me tell you something for finite graphs. So G is a finite graph, and then the Laplacian will just be the usual one. So D is the diagonal degree matrix, A is the adjacency matrix. This is the Laplacian, and okay, and let's say the first eigenvalue is 0. Okay, so let me state something in the planar case, although we'll see that it applies more generally. So now basically I want to say that, I mean, this is some example of where choosing a nice weight function on the manifold gives you bounds on the Laplacian. So what might the analog be for a graph? Well, just take some non-negative function on the vertices, and then just define. Let's define a corresponding path metric. So it's just the path metric weighted by this omega. So the infimum of this is just the sum of the vertices in the path gamma with their associated weight, such that gamma is an xy path in G. Okay, so that's a definition. So now the point is I can take a weight function on the vertices and I can I get some new metric on the graph. And let's define one more thing. Let's define the analog of this area. Let me define it like this so that it will carry over to the unimodular setting. So this is just the expectation over a random vertex of. Okay, so the L2 norm I'm using here is the expectation. It's sort of the capital L2 norm on the vertices. The expectation of omega x squared. Okay, so now if you have this setup, let me give you an example of what one can do, and then I'll tell you how it relates to Benjamin Schramm. So let's define some collection of nice metrics of this form on a graph. So I'm going to take all of the metrics such that, such that the following holds. That if I average this weighted path distance over everything in this set, this is supposed to be an S, then I want this to be at least, let's say, okay, at least what it would be. So at least this is a two-dimensional average. So if I take any set of, for instance, if I take any set of points in the grid, in the standard, say, integer lattice in the plane, then I would have such an inequality up to some constant. Well, the average distance would have to be at least, if you put some constant here, the average distance, according to the isometric inequality in the plane, would have to be at least square root the number of points. These are good points. No, they're not good points, right? Yeah, no, it should be. If I take a ball of radius r, it'll have r squared points in the plane, and so the average distance will be r, which is square root of the number of points. Yeah, so it's okay. We've all just had lunch, and unlike me, not everybody just had 3 coffees. So. Yeah. So, I didn't say. Yeah, good point. Thank you. You can ask me in English if you want. Yeah. So there's a k. The k doesn't right now refer to anything. This is for all sets of measure 1 over k. So all sets of size k. Okay. So what I'm doing is I'm looking at all of the weight functions, such as the metric. This is I ran out of space, obviously. So just you have to. So that the metric doesn't collapse on sets of size n over k. So it's big on every set of size n over k, the average distance. I'm sort of, if you think about the graph as being, this weight function is making sure that for any large enough set, the average distance in that set, you could put it greater than or equal to n over k here, it wouldn't matter. The average distance in that set is pretty big. Okay, so that's okay. So now here is a theorem of it's joined with Kellner, Price, and Tang. So this is two-dimensional. So this theorem is going to be stated only for planar graphs. That if G is planar, then the kth eigenvalue is bounded up to constants by this ugly maximum degree. Will make a reappearance in a second. By the maximum degree times the minimum L2 norm of any weight in this family. So the point is that if you want to bound the kth eigenvalue of some planar graph, it suffices to find a weight function with small area that is non-collapsing on all large enough sets. No. So in fact, this is not that hard to prove. And this is always okay. And in fact, this is always there always exists a weight function that makes this quite small. So yes, k over n. Okay, so like this is a say it again. Both are non-trivial. If you wanted to prove this one by itself, for general graphs, for instance, you have to lose like this. You have to lose a log n here in the number of vertices. But this is the more interesting one. Well, okay. We're going to talk in a second about recurrence and transient, so that losing any logs is bad news. Okay, so that's so the point is, I mean, this is just this philosophy taken to some far point. And okay, so now where's the symmetry? Where's the unimodularity? So what is the so the result of Benjamini and Schomer I'm referring to is the recurrence theorem. The recurrence theorem, which says that if G is okay, I decided that it's a obviously they didn't call it a Benjamini-Schrum limit. If G is a Benjamini-Schrum limit of finite planar graphs with uniformly bounded degrees, then G is almost surely recurrent. Okay, so that's the. People have been talking about the distribution limits the whole week, so I'm assuming that people know what it means. But yeah, so you take some weak local limit of a bunch of finite planar graphs that have a uniform bound on degrees. What you get the random walk is recurrent. And just as a reminder, this means that the green function diverges. Right. So this holds almost surely. And well, the starting point for my interest in this is that if you look, you can actually see a clear connection between these two. If you look for long enough, you can see a clear connection between these two things because, okay, let's just take a finite planar graph and do the following, and just let's look at the average return probability. So by the way, yes, as nobody asked, so this is the probability that the random walk starting at rho is at rho after t steps. Just the discrete time heat kernel. So, right, so in the finite case, this is just, what is this? This is just, 1 over n times trace p to the t, where p is the transition matrix of the random walk, which we can write in terms of eigenvalues. Eigenvalues start at 1. If we write it in terms of eigenvalues of Laplacian, it looks like this. And now an easy way to lower bound this is just to look at how many eigenvalues are smaller than 1 over t, because every one of those will give us a constant contribution to this sum. Right, so that's okay. So we can come over here and just check that the number of eigenvalues smaller than 1 over t is up to the degree it's n over t. So set k over n equals 1 over t, and then k is equal to n over t. Okay, so there is this factor of the maximum degree, and there's a constant here. But then you get that was just 1 over the maximum degree, right? And the point is, so the average return probability is 1 over t, and like that sum diverges. The sum of 1 over t from t equals 0 to infinity diverges. So, I mean, this suggests very strongly that that one could prove the Benjamin-Strom theorem along these lines. It's no, I don't think so, because yeah, I mean, you can come up with you need some weak, like even first moment type concentration. You could have that the return probabilities are dominated by some small set in the graph, and then with constant probability in the limit, you just split into two things, and with probability half you see one thing and probably half another, and this contribution could all come from half of it. So like this contribution could come, if only half the vertices satisfy this lower bound, then it's still true up to a factor of a half. So it could be that half the vertices, you could have a half of a thing being a planar graph and half being an expander or like an infinite tree, and you would still see this along the way. But then in the, okay, so yeah, so you need some version of this that sort of holds everywhere, but at least more, I mean, which you can prove. I mean, there is a right. You can prove that, but I'm just saying morally there's a connection here. What's more disturbing is okay. There's a beautiful generalization of this theorem to the cases when the degrees are not uniformly bounded, and the motivation for that is comes from this model UIPT. So this is the infinite random graph that's the distributional limit of random planar triangulations. Right. So this is the Benjamin-Strom limit of random triangulations. I mean, as introduced formally by Angel and Strom. And if one wants to talk about, for instance, whether this graph is almost surely recurrent or transient, then the Benjamin-Strom theorem doesn't apply because, well, this graph doesn't have uniformly bounded degrees. So degrees can, I mean, the degrees are, I mean, they're, well, that's unbounded, yes. So what Asaf and Ori proved, you know what, if you have two names separated by a dash, then I reserve the right to summarize it. Which is that okay, under the same assumptions except for bounded degree. So this is you have a limit of finite planar graphs. And now the degrees are not uniformly bounded, but you assume that they have sharp tails. So if you make this assumption, then you get the same conclusion that G is almost surely recurrent. Okay, so that was a long-standing open problem that appears in various forms in the literature on quantum gravity. That's their name for it, not mine. Not their name for it. That's the people who study its name for it. Yeah. So the point is that this doesn't seem to give something here because, I mean, you have a bound that's degrading with the maximum degree, and so what's just sort of almost an observation from. I don't know if Nadi remembers. I asked Nadi some silly question at Yuri Matushek's memorial conference. I asked some silly question about sort of getting better bounds on eigenvalues in terms of degrees. It was silly, but in the sense that it was clearly false. But there is something. Okay, but there is something one can do that is actually fairly straightforward, which is just. So the way this bound is proved is just that one takes this weight and then constructs k disjointly supported test functions. So, and then each one of them has a bound of k over n on the Rayleigh quotient, so you get a bound like this, because disjointly supported functions are orthogonal. So now if you want to get something better in terms of the degree, just take 2k such disjointly supported bump functions and throw away, say, the k with the largest degree. So then, what, like if you do that, what do you get? well, you get some bound that's depending on the kth largest degree times k over n. So this is just not the maximum degree, but throw away the vertices of, well, I don't know, it says kth, so the vertices, the k minus 1 vertices of largest degree. I mean, this d max here is just coming from a trivial bound of, like, you pay, if a vertex has large degree, you pay that in this bound. So if you have 2k disjointly supported functions, and you throw away all the ones that are supported on a vertex of high degree, then the bound improves. And now you can just check if the graph has exponential tails. I mean, look at what does it mean for a finite graph. Then, so by the way, what do exponential tails mean? The probability this is bigger than lambda decays like e to the minus constant times lambda. That's what exponential tails means. So under, this is just in the finite case, but if you look at sort of empirically what it means to have exponential tails, then the bound you should get here is log n over k times k over n. Because yeah, because I have n over k chances to, let's see, why is that the bound you should get? Oh, right, because if I want, why is that the bound you should get? This is when you ask the audience, does anyone see why? Say it again? No, log n, I know, I'm looking at the k largest. So the point is, I have k eigenvalues bigger than this. So what's the probability of that? Yeah, okay, it's just a union bound. I mean, it's just the probability of this is yeah. I don't know why I'm making that. I decided to make this so complicated. Yeah, I mean, take e to the, there's an implicit constant here. So e to the minus this is n over k. Yes, it's what Omer said. Like this is the bound you will get. Like the probability. I mean, you have n chances, and but I want k of them to succeed. So if in order to have their sort of expectation come out correctly, I should take the bound to be log n over k here. That's supposed to be that was supposed to be trivial. Okay. So the point is now if you do this and now you plug in you plug this into this argument, then what you get here is that instead of seeing let's see. So now we've bounded the number of, it's independent of degree. So what we get is instead of 1 over t, we get 1 over t log t. Because remember here, we're looking at the number of eigenvalues less than 1 over t. So that's going to be now, instead of n over t, it's going to be n over t log t. So just this implies that the average return probability is at least 1 over t log t, which is now still great because that means that like this sum still diverges. So okay, and like I said, you can work a little bit harder and actually, instead of not just make these proofs moral, but actually rigorous proofs. And for instance, you can say that in this model, here, yeah. So this was for any limit of graphs where the degrees have exponential tails, but in particular, like for you get that. Yeah. So if you look at this, you get some concrete rate of decay here. So if you sum this one from t equals 0 to t, what you get is log t. And so okay, I wanted to ask. So I will tell you in a second where the unimodular change of metric came in. This was just change of metric for finite graphs. But one interesting question is, actually, it was conjectured in the 80s for this model for random triangulations. Well, at least it was suggested by experiments run on computers in the 80s that actually that actually this should still be like log t, as if it was 1 over, as if the return probabilities are 1 over t and not 1 over t log t. So that's it. I mean, so this is false in general. This is false if you only assume that the degree has exponential tails and you have a limit of planar graphs. So you have to use something additional about UIPT for it to be true. But well, that's an interesting question about what the right rate of decay is. Okay, so now let me say. Well, okay, I shouldn't call it a conjecture. It's just a question. No, this is on. So for UIPT, does the green function? I mean, does it diverge like log t or log t, or something in between? There's a paper from the 80s with experiments that suggests that it's like log t. Experiments were much worse in the 80s. So I assume one can do them now and actually basically determine with pretty high confidence, distinguish between these two asymptotic rates. Okay, so if you want to make this all very clean, so everything here was finite. So here is something nice you can do. So take some again unimodular random graph, and you can look for the best sort of weighting. I mean, for various purposes, but you want to sort of try to find some weighting that makes the geometry of the graph look nice. And a very natural thing to do is to try and make the growth rate of the graph as make the graph have a polynomial growth rate of as small degree as possible. Okay, so let's. So I want to consider. So I have a unimodular random graph. I want to consider triples like this, where the triple itself is still unimodular, which means that well, it satisfies a mass transport principle, where the flow can also depend on this omega. But in everything I'm saying here, you can just think of it just take a distributional limit of weighted rooted graphs, and then I'm considering such things. So it's the whole triple has to be unimodular. And let's think about just normalized metrics. So the analog of this L2 norm also makes sense here as just the expected value at the root. Okay, so now you can. I mean, this is the kind of thing that's done a lot. I mean, there is this notion of Pansu called the conformal dimension of a metric space, where you take a conformal reweighting of the. You should probably take a metric measure space. Take a conformal reweighting of the metric, and then you try to say make the Hausdorff dimension as small as possible. So this is one could consider something like this as a discrete analog. So the growth rate of some unimodular random graph is basically the best rate of volume growth one can achieve with a normalized metric. So let me assume that all these metrics have norm at most 1. And well, I don't need to assume that. So to take the infimum over unit area metrics, and then I don't know, some limit of the size of balls. I'll explain what that L infinity norm is in a second. I mean, okay. You don't have to understand exactly the definition. It's sort of, I'm taking, I'm computing the asymptotic growth rate here. So this is the essential supremum, meaning that I require that almost surely, whatever bound I'm going to use on the size of the balls around the root, I require it holds almost surely over the choice of G and rho. Okay, so like this is an L, I mean the weight is bounded in L2. the size of the balls has to be bounded almost surely. So if you define, so now if you sort of try to extend this theory in a nice way, here is the kind of result you get. This is the definition. This is the conformal growth rate of the graph. So for instance, it's not completely clear, but if G is the distributional limit of finite planar graphs, then the conformal growth rate is always at most 2. That's yeah. So good. Yeah. So first of all, this is the dimension is a function of the law of this thing. This is not a random variable. This is a function of the law of G comma rho, and I'm using notation. And then I'm taking infimum over all omegas such that this triple is unimodular as a random marked network. And then I'm calculating the best, the asymptotic growth rate. The limit may or may not exist. Let's ignore such issues for now. And then let me remind you the definition of the spectral dimension. Okay, so the spectral dimension of a graph captures just the decay of the return probabilities. So if the return probabilities are 1 over t, like we computed for in the planar case, then the spectral dimension is going to be 2, but that doesn't make sense. It does make sense. If you write it correctly, it makes sense, is what I meant. Yes. Now the spectral dimension is 2. That's always worrying from the definitions if you just reason backward to get what you want. So here so here G is just a fixed graph. X is an arbitrary vertex. So this limit exists, and it's the same for every base point. And then a generalization. I mean, sort of if one kind of follows through a similar set of steps to what I demonstrated before, then here is the sort of a kind of nice general theorem that so if the degree is if the distribution of the degree is not too crazy, so has all right, it doesn't really matter. Let me say nice tails, and I'll just say in words, nice means that the tails go to 0 faster than any inverse polynomial. So it's much weaker than exponential, being nice. I forgot, what did they call this in Fourier analysis? Does anybody? When you go to 0 at infinity faster than any polynomial? Tempered. Say it again? Yeah, Schwartz class. But I also think that they, yes. Yeah, so if this is true, then I guess I should write. Then almost surely the spectral dimension of the graph is bounded by this conformal growth rate. So in general, it's just the same philosophy. A nice metric on the graph gives you control on the random walk. And just let me mention. So for instance, if G is the limit of graphs that are, say, sphere packed in RD, so like planar graphs have of course by the Kebe, Andreev, Thurston have a packing in R2. But in general, if you have a packing in RD, then this is a theorem in the sense that it's non-trivial to prove it. Then the conformal growth rate is bounded by D. Okay, so I'm not telling you why. I'm just saying that this is an example. So for instance, this says that if any limit of graphs sphere packed in RD, sphere packed here, by the way, have like quasi-sphere packed also works. You don't need spheres. You just need bounded overlap. You don't need to take RD. You can take any alpha or deregular metric measure space. But then you get non-trivial bounds. I mean, it was on the spectral dimension, so on the rate of decay of this return probability. So one example where this was open, it was for UIPT. So this shows that the spectral dimension of UIPT is at most 2, almost surely. And then yeah, so let's see. Fairly recently, Gwynn and Miller have shown that this is tight. So also there's a lower bound. So now we know that the spectral dimension of this thing is exactly 2. This, so in the remaining, say about 20 minutes of the talk, I will refer to some results as using basically this coupling between models that are related to Louisville quantum gravity, sort of a long line of study of Scott Sheffield and then Jason Miller and Scott. This uses, but which I don't understand, so I'm just going to refer to them as magic. So this is like this uses magic. Okay. I mean, okay. So that's. Yeah, I mean, of course, the best model, the best one can get under these sort of just. If you just know planarity and have nice tails, of course, this is in general the best kind of thing you can hope for because, I mean, well, like the integer path has satisfies all those assumptions. Then it has spectral dimension 1. Okay, so that's maybe I'll leave this up because I'll come back to this. This is actually fairly interesting for some reason, and maybe I'll come to at the end. But let me give another spectral quantity. Okay, so this was about the heat kernel and eigenvalues. One can also say nice things, for instance, about the speed of the random walk. So by speed, I just mean I want to know how fast the random walk moves away from its starting point. So I would like to know what is the beta such that, I mean, assuming it exists, say as t goes to infinity, how fast does the random walk decay away from its starting point? And then the beta equals a half case. This corresponds to diffusive behavior. Yeah, so it turns out that, I mean, this change of metrics can also gives some nice control on the speed. Let me mention a representative case that follows from work with Jianding and Yuval, which okay, it's going to be so. To say it really, okay. So I want to talk about stationary random graphs. So in fact, I want to talk about reversible random graphs, but it won't matter for what I. Well, okay, reversible. Yeah. So this is a reversible random graph is one for which the law of G is a random graph. X0 is a root. X1 is what you get from one step of the random walk. The random graph is reversible if these have the same law. Okay, so like random walk on percolation on a transitive graph. Okay, so if okay, so this is a planar random reversible graph. Then for every metric omega, and again, I just erased it. Again, one has to take omega so that this whole thing is is reversible as a marked network. So you have to take a, I'm only considering metrics that interact nicely with this thing. By the way, if you want to, I mean, there's a correspondence between unimodular random graphs and reversible random graphs. It just comes from degree biasing the random walk. So I'm not saying, it's just that it's nicer to state it in this setting because it will be like a beautiful statement. Then for every metric, one has the following behavior. If you look at the way that the random walk moves not in the graph metric, but in the conformal metric, then this is at most t times the L2 norm of this weight. So let me just write. Okay. And invariantly amenable. Okay. So just take the graph to be a limit of finite graphs. But yes, as Tom pointed out, you need that. Yes, the complete tree will not satisfy this, so you need some other property it looks for all intents. You need some compactness assumption. So the point is now, if one wants to control the speed of the random walk, it's pretty clear what to do. Suppose you want to prove, say, subdiffusive bounds, that some random walk moves away from the origin slower than t to the 1/2. Then it's pretty clear that, okay, so what you want to do is find some weight such that, let's say, the graph distance is bounded by the conformal distance to some, let's say, to alpha, for some alpha less than 1. Okay, so I mean, what this says is basically that the random walk moves like Brownian motion if you look in the conformal metric. So the expected distance squared is bounded by t. Just assume that the metric is normalized, so this is 1. And so now if you want to get some sort of some speed which is slower than that, then you just need to find a conformal metric where the graph metric is smaller than the conformal metric. Then this will tell you that by some concrete amount. This will tell you that the speed here is t to the 1/2, and therefore the speed here will be better. Is that how math works? Like if I put 1 over alpha here, and then I look at this thing to the 2 alpha, that would be that squared. Okay, hold on, let's think for a second. I want the graph distances. Why would I want the graph distances to be? I want these distances. Okay, that was correct. I want these distances to be bigger. If I bound bigger distances, then I even better bound smaller distances. My apologies for English. My abuse of English, anyway. Okay, you want to do this. So now let me just say, okay, so I'll give you in the last 10 minutes an example of this. But let me just say what the state of this was the last time I spoke. So, for instance, for this UIPT, I'm going to use beta for the exponent. So, a 1/3 upper bound was known. This is due to Itai and Nicolas Courien. And then, when I talked at Russ Lyon's birthday conference last September in Tel Aviv, I mentioned that one can get this just from the assumption. Just from knowing basically the growth profile of balls in UIPT, this already follows. And then Nicolas, I think, basically said that he and Itai only stopped at 1/3 because 1/3 is a nice number, so they could have gone further. So Nicolas and my name is not C. I don't know why I'm not writing out some of these names. Just Marzouk proved that actually you can do slightly better than 1/3. This all happened very fast. And then using this loop quantum gravity magic, the conjectured lower bound was proved in the same paper by Gwynn and Miller. And then a little bit after that, Tom and Yuen actually gave the complete characterization. So now we know this is 1/4. So that was a long-standing overland problem to understand the speed exponent in such graphs. And how does this work? It proceeds by using this magical CRT, like continuous random tree, LQG. It's just magic. If I put more words to it, doesn't mean I understand it any better. To find a conformal weight with the correct asymptotic behavior to give this bound. So, okay. So now, just as one, let me mention one thing that I can do where I can. So far, I didn't tell you about any weight. So let me end the talk by telling you a nice result where I can show you what the weight is. So this is for another sort of widely studied model, planar model. Okay, so this is the incipient infinite cluster. Incipient is such a strange word. What is the definition of incipient? Does anyone know? Tom, it's your invented the language, so can you? Ah, it's like it's crowning. That's okay. Okay, yeah. So so this is the infinite cluster in critical percolation on Z2, except that you don't know. I mean, except that there's not an infinite cluster. So you do critical percolation on the integer lattice. You condition on the fact that there exists an infinite cluster. There's a way to make sense of that. And then that's this. This is again some unimodular random graph. Right. So it's you do critical percolation. And you have to do it in some careful way, but it's not that. I mean, you can just take sequences of larger and larger clusters in critical percolation and take some kind of limit. I don't know if I just made that up, so that probably works though. But in any case, sort of if one wants to study the geometry of critical percolation, this is a nice thing to study. So here's a theorem which actually follows fairly easily from this framework that the speed, that the random walk on this thing is subdiffusive in the graph distance. So this is less than 1/2. That's a theorem with Shishendu. So Keston famously proved this if one considers the Euclidean distance instead of the graph distance. But the graph distance is bigger than Euclidean distance, and therefore it may not be true for the graph distance. And in fact, it's known that the graph distance is legitimately bigger than Euclidean distance in some sense. Well, okay, it's not. This is it's the graph distance sometimes is bigger than Euclidean distance by power. So this is sort of a non-trivial statement. Okay, so how does one prove this? It's very simple. You basically use that, right? So again, we want to find a weight, like a conformal weight, where the total amount of weight we use is say in expectation the square is at most 1, and it's substantially bigger than the graph distance. Okay, so I mean there is a sort of well-known geometry of critical percolation. There is, if you fix some scale, then what happens is that there's some kind of sparse backbone, and then a lot of clusters hanging off from this backbone. So this is the backbone. You can define the backbone formally as the set of you can look at the set of points that can reach the boundary of this square by 2 disjoint paths. But you get some backbone like this. And now you see that if you just want to, say, prove this for distances that are larger than the scale of this box, then it doesn't make any sense for you to put, for instance, conformal weight inside these things. I mean, paths to the boundary of this box are not using these things. So you can just put a conformal weight on the backbone. So when I say conformal weight, I mean you take some function you have to define the backbone in a unimodular way because so you need to take a random shift to get cells like this. But basically, define some function which is constant on the backbone. You have to do this also at every scale. And then what you need is just this BK inequality, which says that the density of, basically there's asymptotically more mass in these bushes than there is on the backbone. And well, that's it. So once you know there's asymptotically more mass inside here than there's on the backbone, then you get some advantage. I mean, this weight is not scaled, so you can set it equal to 1 on the backbone, then you need to scale it so the expectation is correct. But you see that you get an advantage once you're putting weight mostly on, you're putting weight on a vanishingly small subset of the vertices. And therefore, when you rescale it so that it has norm 1, you've gained in the distance. So that's, I mean, that's very simple, but it's, I don't consider any numbers better than any others. But, no, there's an explicit number less than a half that you get. But it's not the right number, and it's based on the sort of the 2-arm, 1-arm exponents that are known for critical percolation.
So what number do you get when you have the FNF?
So yeah, so it's a good. So what you could, for some reason, you could hope that if you know everything, like you look at the hexagonal lattice, that you can sort of get some. I don't know what the conjectured speed bound is. Well, then how am I supposed to achieve it? No, that's the point is like if there was some KPZ relation that predicted the exponent. So you're saying that maybe applying this to that could give you a prediction. I don't know.
I asked the number, and then the second question would have been, do you think that the chance to be?
So it's less than a half also on the hexagonal lattice.
What is it in terms of the arm exponent?
Yeah, I don't know off the top of my head.
Is it written in your paper?
In terms of the arm I mean, look, after the talk we can do the calculation. It's very simple, but it's not particularly informative in the sense that I don't think there's any sense. Well, first of all, in that the arm exponents are far from being able to be calculated exactly. Okay. It's not clear if it's tight.
If you remove these bushes, you get the same speed. Clearly, the bushes slow you down.
No, I mean the bushes. You're getting. Maybe it wasn't quite. You have to do this at every scale, Asaf. You do this at every scale. So the point is, inside these bushes, there's a weight function at the next dyadic power that's putting weight in there. It's not just like you take one backbone. I didn't. It's
so
a.
on each scale you put mass only on the backbone, but you have many scales.
Yeah, I mean, I didn't mention. I mean, yes, if you just prove this for one scale, if you can find one weight for every distance scale, such as this holds for that distance scale, then without increasing the 2 norm by more than a logarithmic factor in the distance, you get it for all the distance scales, just by you make your weight, you sum over scales, and then you do something so that it's going to sum out. Okay. You do something like this, and now you have a weight at every scale, and what you lose, I mean, this thing, expectation of this is, it's 6 over pi or something, whatever. But the point is that what you've lost here is, like, if this weight is supposed to handle scales between 2 to the k and 2 to the k plus 1, then what you've lost here is something logarithmic.
So at which point do you put mass on the bushes?
So you choose your scale. Now randomly partition the whole thing into boxes of side length 2 to the k by 2 to the k. Only once you define the boxes does it define the backbone. Now you put weight on the backbone there. The bushes will get weight at some smaller scale. Oh, yeah, so here, everybody is a bush to someone else, right? Okay, so just one interesting open question that you can ask here is, so these upper bounds, because they use this sort of magic, the magic for reasons that I don't fully understand, doesn't work out as well for other models like random quadrangulations. So you could still hope that a more robust method like this would give these bounds. And yeah, it's probably the case. So I mean, I don't like here. You see that. So Itai at some point long ago suggested that like this thinness of geodesics is a fundamental obstruction to sort of diffusive speed. Right. Here, there's a topological obstruction to. I mean, I can't get out of this box without walking on the backbone. But you can imagine that that there's a backbone, and then there's some. You can imagine, and then there are some ways out, but they're much longer. You can imagine sort of like the sort of almost geodesic backbone. And it seems not implausible that if you do some generalization, one can prove these speed bounds for, say, random triangulations using a similar kind of method, basically saying that there's a vanishingly small measure of things that of vertices that lie on really good really good paths, and that all the other vertices lie on paths that would be sort of that are very long. And then by trading this off, you can see that you put most of your weight on these things, some vanishing less weight on those, and so on.
Even if that works, you only get one bound.
You only get one. Oh, you only get an upper bound. Yeah, all these things only work for upper bounds.
Do you have examples that's completely off? The conformal, what you get from the conformal growth and the...
Yes, I mean in the sense that, I erased it, but in the sense that the spectral dimension is bounded by the conformal growth rate, but it's false in the other direction. There is an example that's in the paper of, who are the authors? It's Tom and Asaf and Omar and there is an example of in fact, something with infinite spectral dimension that has bounded conformal growth rate. Yeah, that's probably false. Oh, right. Okay. Yeah. So yeah. Okay. So the point. Yeah. So okay. Something the other way around. So something that has infinite conformal growth rate but bounded spectral dimension. Just because the random walk gets stuck in these pockets, like there's a big piece of the graph that it's impossible to make the growth rate small, but the random walk gets stuck in pieces of the graph where it gets stuck. So yeah. So there can be big gaps. Although I did try to prove some converse to this, which is that so in that example, in that example, if you look at say this expectation, then the contribution to the expectation comes from a very small set of vertices. Right? There's so if you assume that the return probabilities have more concentration, then you can prove some kind of converse if you assume a strong enough concentration. Yeah. So here's one thing which here. I've already said let me end 10 times. So let me really end with the following thing related to Roman's talk and some non-conformal weightings. So I never thought. So actually, these conformal, these vertex weights are not very useful for actual groups, for actual transitive graphs, and that's just because, most of the properties, including the growth rate, are convex. So they're maintained under averaging, and therefore the best thing you should take on a group is just the uniform weight. But then it struck me that actually, so now if you actually consider edge weights for groups, then sort of like you can do all of the. Here's what I would like. So as was mentioned, if you try to prove Gromov's theorem in a completely finitary way, so just for finite groups of polynomial growth, the big problem is that it's hard to find a scale where the growth is doubling. So where you have some relationship between balls of radius 2r and balls of radius r. It's hard to find such an r, and in fact, it's still essentially non-effective how small you can choose this r to be in terms of the other parameters. Like you might have to take the radius to be extremely big. And the reason you do this is because at this scale now you can basically, well, you can do something spectral. So you can bound the multiplicity of eigenfunctions that are supported, say, on this 2R ball. And then there's, using sort of a finitary version of Kleiner's proof and some elementary group theory like Jordan's theorem, everything goes through. Really finding this scale is the hardest part. And it's actually not clear to me now that what you can't do is, like, there's no reason, basically change the metric on the group so that you don't find the scale where it's doubling. You find the metric where the group is doubling at some small scale. And then actually, all the stuff I said about eigenvalue bounds, that can also be used to bound the multiplicity of eigenvalues. So that's not really an open question. That's just some interesting direction. Okay, let me stop. Thank you.
So when you're saying changing, using edge weights, it's important that for different.
Yeah, so
the
it's,
hope you don't touch, right?
say it again. Yeah, you don't.
Hope you don't touch.
You don't. Yeah. So I mean, you can, if you just think about choosing edge weights so that the L2 norm is bounded. If you could choose edge weights so that L2 norm is bounded and the metric is doubling, you can actually. I'm pretty yes. In this case, you should be able to sort of construct a spectral object that gives you a representation of the group acting on a small dimensional subspace.
I don't see how. So can you change the metric on the edges in a way that you cannot have?
Yeah, you can imagine, because you can give different generators different weights. So, for instance, if I had some virtual piece sitting there, I could maybe find a way to get rid of it, contract it or something.
Okay, let's think again. We meet again at 4.